Okay, so we hear the term greenhouse effect thrown around constantly, right? But what does it actually mean? We're going to break down the basic science that runs our planet's climate system and figure out exactly how carbon fits into the whole story. All right, let's start with a little thought experiment. Imagine you could just poof, get rid of Earth's atmosphere. What would happen to the temperature? Well, it would plummet to a shocking minus 14 degrees Celsius. That's about 0 Fahrenheit. We'd basically be living on a frozen, totally inhospitable ice ball. But thankfully, that's not our world, is it? Because of our atmosphere, the actual average temperature is a much, much nicer 15 degrees Celsius or around 59 Fahrenheit. I mean, think about that jump. That incredible difference is all because of the natural greenhouse effect. So here's how we're going to tackle this. We'll start with Earth's natural thermostat. Then we'll get into how the whole greenhouse thing works and meet the key gases doing the work. After that, we'll dive into the enhanced effect, check out its ripple effects across the globe, and wrap it all up by looking at the human fingerprint on the system.
Okay, so first things first, let's get one thing straight right off the bat. The greenhouse effect itself, it's not the bad guy. Not at all. In fact, it's the absolutely essential process that makes life on Earth possible in the first place.
So what is it exactly? Honestly, the best way to think about it is like a planetary blanket. The greenhouse effect is just this natural process where certain gases in our atmosphere, they trap heat. They stop all of it from just bouncing back out into space. And that keeps the Earth's surface at this nice, cozy, life-sustaining temperature. But how does this blanket actually work its magic? Well, it all boils down to a pretty simple four-step exchange of heat. Okay, step one. The sun's energy zips down to us as shortwave radiation. It passes right through the atmosphere, no problem. Step two. The Earth's surface soaks up all that energy and, you guessed it, it heats up. Step three. Now that the surface is warm, it radiates that heat back out, but this time as long-wave radiation. And now, here comes the most important part, step four. While some of that heat just escapes into space, those greenhouse gases we talked about, they catch some of it, and they send it back down, trapping it and keeping the planet warm. It's that simple. So, what exactly are these gases that make up our planetary blanket? There are a few, but we're going to focus on the two main players. Think of them as the two biggest dials on our planet's thermostat, carbon dioxide and methane. And when you look at them side by side, you see they're really different beasts. You've got carbon dioxide, CO2, which mainly comes from burning fossil fuels. It's like the marathon runner. It hangs around in the atmosphere for centuries, making it the big, long-term driver of warming. Then you have methane, CH4, which you get from things like agriculture. Methane's the sprinter. It's gone in a couple of decades, but man, while it's here, it's a powerhouse. It traps heat way more powerfully than CO2. Okay, so we've established the natural greenhouse effect is not only good, it's essential for life. But what everyone's talking about today is the enhanced greenhouse effect. And this is where we humans enter the story and start cranking up that thermostat. You know, for pretty much all of human history, there was this nice, natural balance of these gases in the atmosphere. The game changer, the real turning point, was the Industrial Revolution back in the 1800s. That's when we started burning fossil fuels on a massive scale, and that lit the fuse that led directly to the sky-high concentrations we're seeing today. And the sources of all these extra emissions, they're no mystery. Burning fossil fuels, coal, oil, and gas is the #1 culprit, pumping out huge amounts of CO2. Chopping down forests makes it even worse, since we're getting rid of the trees that would normally soak that CO2 up. And then you have things like farming and our landfills, which are major sources of that other big one, methane. So here's the key takeaway, the most important thing to remember. The enhanced greenhouse effect isn't some brand new thing. It's just us amplifying the natural process. We're adding more of these gases to the atmosphere, and that's like throwing a thicker and thicker blanket on the planet. And the thicker blanket just traps more heat. So what happens when you have this thicker blanket? What does that actually do to the planet? Well, it's not as simple as saying, oh, things just get a little warmer everywhere. This extra heat kicks off some really complex ripple effects that travel through our entire climate system. And maybe one of the most crucial things to get is that this warming isn't spread out evenly at all. Not even close. If you look at the polar regions, for instance, they're heating up way, way faster than the global average. And there's a really specific reason why. It's because of something called a feedback loop, specifically the ice albedo feedback loop. Think about it. Bright, white ice is like a giant mirror reflecting sunlight back out to space. But when that ice melts, it reveals the dark ocean or land underneath. And dark surfaces don't reflect heat, they absorb it. So the darker surface absorbs more heat, which melts more ice, which reveals more dark surface. You see where this is going? It's a cycle that just feeds itself, supercharging the warming at the poles. This extra heat messes with our weather patterns too. See, a warmer atmosphere can hold more moisture, more water vapor. That basically puts the water cycle on steroids. It means you get more intense, heavier rainfall in some places, but at the same time, it can shift these big atmospheric currents, which can cut off the moisture supply to other regions, leading to worse and more frequent droughts there. And here's another one of those critical feedback loops for you. As the poles get warmer, the permafrost starts to thaw. Now, permafrost is ground that's been frozen solid for thousands of years, and it has tons of methane locked inside it. So when it thaws, that methane gets released into the atmosphere. And what does methane do? It traps heat, causing more warming, which, you guessed it, thaws more permafrost. It's another one of those cycles that just keeps feeding itself. Okay, so let's pull all these threads together. Let's look at the clear, unmistakable human fingerprint that connects the cause, our emissions, with the effect we're seeing on our climate. Honestly, nothing shows the change better than this. Take a look at that first bar. That's the normal level of CO2 in the atmosphere for like thousands of years before we started building factories. Now, look at the second bar. That's where we are today. The sheer scale of that jump, it's just dramatic. It's undeniable. When you boil it all down, the takeaway is incredibly clear. It's a straight line. We add more carbon to the atmosphere, that traps more heat. And that extra heat doesn't just nudge the thermometer up a bit. No, it fundamentally rewires the global climate patterns that everything, our ecosystems, our societies, is built on. Look, the basic physics here, it's solid. The data showing we've enhanced this effect, it's straightforward. The science has clearly connected the dots between atmospheric carbon and our changing climate. So, the real question isn't about the science anymore. The question it leaves us with is, what do we do now? What happens next? That part is up to us.